Hey, howdy everyone. I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin, where I teach and conduct research on data analytics, geostatistics, and machine learning. And I record all of my lectures and provide them to my students and anyone else interested to learn about these topics. All right, so we've already described the concept of a loss function. We've talked about the idea of training a model as a minimization of the loss function. And we just got through talking about ridge regression. Now we've introduced the lasso or the lasso, depends if you're British or American, I think, regression methodology. And we have to now get into numerical optimization. Now, this is going to be a very basic coverage of this essential topic. We're just providing some context to be able to move forward. Why? Because many of our machines that we will encounter in this course will use numerical optimization to train the model parameters. And we will have specific parameters associated with this numerical optimization, such as momentum and step size or learning rate, that we should understand. And so I want to introduce it in a very simple, accessible manner. There's plenty of stuff we don't have time to get into. So I apologize, this will be somewhat cursory. All right, so let's talk about it. We're moving away from ridge regression to lasso. And the main difference between the two methodologies is that in the loss function, we switched the regularization term from an L to the sum of the squares of the coefficients or model parameters to an L1, which is just the sum of the absolute values. Okay, so in doing that, for all generality, we've now lost access to a simple analytical solution. It's not all lost. We can still solve the problem. We're just going to have to rely on a numerical solution scheme. And so specifically, we'll get to it and we'll talk about gradient descent, stochastic gradient descent as the methodology. It has been demonstrated that lasso solution is unique for any number of features. So we know that this is going to, we have hope that it should work. Now, the assumptions being that all features are continuous and the loss function does in fact have a global. Let's talk a little bit about loss functions, just a little bit of a review for you. If we go and we think about the lasso or lasso loss function, this is what it looks like right here. This is just the residual sum of squares. And this component right here is the regularization term right here, where we're trying to drive the parameters to be smaller, and we put some weight on that, a regularization coefficient, in fact, lambda. Now, we could take that loss function and we could just simplify it down for the case in which we're working with 1, m equals to 1. There's only one predictor feature. And if we did that, we would get this as our loss function, very simple. We'll go ahead and just focus on the slope coefficient, and we'll start looking at how we could change that. Here's a steeper slope. Here's a low B1 value. And I think we could see immediately that if the slope was too low, we would expect to see a loss function value that's pretty high. It's getting kind of high. And if we use the medium slope, it's more kind of a happy medium, and we have a lower loss function, and we have two samples. And we could imagine that underlying this, there is going to be some type of function over possible values of B1 with loss function values that are going to be decreasing. We'll have an optimum or lowest amount of loss, and it would ramp back up. Now, ideally, in training our model parameter B1, we want to find that one B1 for which we minimize this loss function. Finding that best model, the one that minimizes the loss function, is going to minimize the error in training under the constraint of regularization. And this is an optimization problem. It's an optimization of the model. And so we want to find the optimum model parameters to minimize the loss function. Training the model parameters is optimization. Let's start out by talking about the happy case where we have a access to an analytical solution for optimization. We don't have to rely on a numerical iterative scheme. This is the case of ridge regression, linear regression. It's well behaved. We can just go ahead and solve it. What we're going to do is we're going to look for model parameters that minimize this loss function. We'll optimize, but we can do it with the analytical solution based on the first and second derivatives of the loss function. Criteria we're looking for, locations where the first derivative is equal to 0. First derivative equal to 0 indicates that you have a 0 slope. In other words, we have a transition from going negative to positive slope or positive slope to negative slope. That indicates that we may have a minimum or a maximum, and we don't know. It might be global or local. Now what we can do is we can look at the curvature. Now if we look at this curvature, it's the change of slope is always increasing, going from negative to positive. And so we're looking for a location where we have a positive slope. That will indicate, that's how we're going to be able to tell the difference between a minimum or a maximum. We have 0 slope, it's a minimum or maximum. When we have positive slope greater than 0, we would expect it to be a minimum, and that's exactly what we're looking for. Now, we could look at the first derivative of this function. It's a quadratic in this case, so it will simply become a line. And we can very clearly see where we cross the 0 slope is right here. And if we take the second derivative of a quadratic, it becomes a constant value, i.e. it's just constant curvature over the entire range that we're considering. In the case where we have an analytical solution available, we can just simply use the derivatives to figure out if we have a minimum or maximum, and use the second derivative to go ahead and determine which it is. Now, none of this is proving whether or not it's a global or local minimum or maximum. Now, there's a methodology as we get into numerical solution methods where we don't have access to a nice analytical form. We can just go ahead and brute force the problem. It's known as grid search. Now, if we go back to the case of having one single model parameter, we could bin up the possible range of model parameter. We bin it up and we just calculate the loss function for all of those. And then we can go ahead and plot it. Effectively, what we're doing is we're just looking for the very lowest loss function value, and we'll take it, but you could plot it and look at it, and that would be interesting too. Now, this is possible in the case where we have one model parameter. In fact, that's pretty simple. We could just run it and get many results and sample our way to the problem. The problem is that most of our machines are going to be based on a large number of possible model parameters, and the combinatorial is going to blow up on us. This is similar to the issue we had with the curse of dimensionality. If we have 2 model parameters, well, if we needed 10 bins here, now we have to sample at 100 bins. In fact, the number of the combinatorial will be equal to the number of bins in each model parameter to the power of the number of parameters we want to work with. Okay, so it's going to blow up. It's going to get too large. In fact, it even gets much worse if we're using Bayesian approaches where we're considering the uncertainty of all the parameters. That becomes a very vast space, and we will struggle with brute force. Okay, what's our option? If we don't want to use brute force because it's too big, it's too hard to do, what we can do is we can use a methodology like a gradient-based optimization. The gradient-based optimization is a really good idea. What we'll do is we'll randomly start at a location on this function. So right here, this is iteration number 1, time 1. We have this location right here. You calculate the loss function, so we got the loss function value right here. Then what we need to do is we need to calculate the loss function gradient. You want to know what is the slope locally at for that selection of a parameter at T1. Now, remember, we don't have an analytical solution to the loss function, so we typically won't just be able to solve a derivative to get the slope. what we're going to do is we'll do numerical differentiation. We'll just go ahead and calculate the derivative by using an epsilon offset down and up in that one along that one model parameter. And right here, this will give us the derivative, whether or not it's this way positive or this way negative. Then what we can do is we take that derivative and it's telling us which way is downhill. In fact, the positive derivative is taking us uphill. So what we'll do is we'll take that previous value of the estimate of the parameter. We'll take the negative, because we want to go downhill, not uphill, of that gradient, which is this value right here, and we'll apply a learning rate. It's also known as a step size. I like learning rate. And it'll tell us how far do we want to offset. But you'll notice it's updated by this magnitude of the gradient. In other words, if the gradient's very steep, you'll go further. If the gradient's very shallow, you'll go not so far. And so it's adaptive. That's pretty cool. Now we got to pick a learning rate in order to do this. But at this location, we have a pretty steep gradient. Our next step will be downslope to here. There's T2 time 2. Then we'll have another step, not as far as the first step because the gradient is getting shallower, and we know that from a quadratic. We would expect that. And then the next step, we start to slow down. And so we can see that we're starting to converge in the minimum, the local or global minimum. In this case, it's quadratic. We know it's going to be the global minimum. Okay, so that's what we're going to do, is we can go ahead and step down slope adaptively from the standpoint that we'll take bigger steps in steeper gradients and shorter steps in the smaller gradients. Let me just make a couple of comments here. First of all, how does it converge? Well, you can see that in this case right here, that we're able to find the minimum value. It's going to reach a point where it'll stop stepping. You can put a tolerance on it. You can stop. Now, we know we're going to find a minimum. We don't know whether it'll be a global or local minimum, but we will find a minimum with this methodology. What about the gradient search step size? Well, the learning rate or step size are, if it's too small, it's going to take too long. You'll take little tiny steps. It's going to have to run many iterations to be able to get to the minimum. The other thing is you could use too large of a step size. Now, technically, you may skip over the global minimum and find a local minimum if it's too large. That could happen. Something that's more significant is we could diverge. Now, let's do this. If I start right here, that's my initial guess, and this gradient is going that direction, but I put a very big step size. I'm going to jump past the minimum, and I'm going to go up the other slope higher. Now, because I've gone higher, now when I estimate the gradient there and I take my step, it's a bigger step back the other way. And I end up even further away from the minimum. Now the gradient is even steeper. And so I go back the other way, but I'm going to go back even further. Boom, boom, boom. And literally our solution will blow up. We will not be able to converge. We will diverge. Okay? So this can happen too. So if you have that problem, you need to use a smaller step size. Now, what about multivariate optimization? Because I know our machines don't have just one model parameter. We're just doing that for demonstration. And we're going to work with many parameters. So what we can do, in fact, it's not a big deal. We can calculate and decompose the gradient over multiple parameters. Now we have a vector representation. So not so bad. So we're at this location right here, T1. We can calculate the gradient relative to B1 parameter, calculate the gradient relative to B2 parameter, and we can represent that as a vector of gradients right here. And so our step can be the resultant of the two in the two parameter components. Not a big deal. So we can do that. We can calculate them separately and put them together in a vector. The optimization, we're training the machine learning model by exploring or walking through this high dimensional space looking for the global minimum. That's what we're going to be doing. That's our challenge we need to face. What about global versus local minimums? The first comment I'd make is you really can't tell the difference. Not in generality. In fact, recall, we don't have that loss function, what I showed right here. I don't have those contours. What I just have is a couple of samples along a path. And you have to remember that this is a vast solution space over all of the combinatorial of possible model parameters, and there's always the chance there's a better solution that further minimizes the loss function elsewhere. There is an exception for convex loss functions. We can guarantee a global minimum will be found. Now, what does a convex loss function mean? Not a big deal. If you take any two random points on a loss function, if the segment, the line segment that connects the points is always above, doesn't cross the function in this case, then we can say it's convex. Now we could flip it upside down and say we're always below, but the main point is we don't cross the function. That's a convex function. A non-convex function is not a convex function. In other words, we have segments that cross the function when we connect any random 2 points. Now, if you think about it, it does feel like it's a little bit of a kind of cheating, kind of trivial, because we can immediately recognize that in the case of a convex function, you don't have local minimums. You just have the global minimum. You don't have these right here, would be a local minimum, where we have a better global minimum here. That occurs with non-convex functions. So we have some cases for models in which we know that we'll have convexity, and then we know that all of our solutions, our minimums, will be global. How are we going to mitigate this problem of being stuck in a local minimum? One of the ways we do this, which is quite practical, is we seed multiple random starts to the parameters. In fact, if we were to go ahead and start here, our gradient descent would likely get trapped in this local minimum right here. But if you could imagine, if we were to seed enough random starts, we'll explore the solution space and we would find this one right here. How do we know the difference? Not a big deal. We can calculate the loss function here, the loss function here, and we know that the one that minimizes over all of those is going to be our best estimate of the global minimum. What else can we do in order to try to improve our robustness to ensure we don't get stuck in local minimums? There's more complicated methodologies. We could start with a large learning rate, step size, and we could reduce it over the steps. This is done often some type of adaptive approach, and the idea being early on you can explore over the loss function without getting trapped. You can skip over these little local minimum and hopefully land in a global minimum as you start to shorten the step sizes later on. So you start big step sizes so you can survey around and skip over local minimums, and then you have smaller step sizes later and you'll be able to converge on the global minimum. That's the idea. Now there's a lot of other ideas around this. The Atom optimizer, commonly used in artificial neural nets, available in TensorFlow. It has a step size that's adaptive over the iterations based on local window variations. And so we could have an adaptive approach that tries to account for the noise, local noise in the loss function. That's super cool. That's very cool. Simulated annealing does something very cool, and that is it has a probability of accepting bad steps. It can go uphill, but it uses a probability of accepting bad steps that decreases over time, so it's able to start converging, explores at first, and then it starts to converge later on. Very powerful methodologies. What's another methodology by which we can improve the stability of our solution? One methodology is the concept of momentum. And if you think about momentum, you imagine a marble going down a complicated surface. That's exactly what we're trying to capture here. We have a momentum coefficient shown as lambda here, and it is the weight that we put on the previous step to infer the next step. How does that look? The equation is shown right here. The step that we're going to take is going to be a function of the learning rate times the gradient. What we're going to want to do in order to go from t minus 1 to t is we're going to use a weight put on the previous step. Now this is a vector, it's got direction and distance. We're going to put 1 minus that weight on the current step based on the instantaneous gradient at that location. So the last step, if you look at it, it was from here to here. We take that and we just copy and paste it right there. We say, well, we kind of want to keep doing that. That's momentum. But then when we calculate the local gradient, this is what it looks like. So we do a weighting of those two. If we use a large lambda value close to 1, we're going to basically have like a freight train going down the track. It can't make very sharp corners. It's going to want to keep going straight. And if we have a very small lambda, we'll have something that can react immediately to the gradients. And now we're going to try to fit the best momentum value to improve the solution. Now, if I tried to, represent what that would look like, imagine if I had a half pipe, and I mean like literally snowboarding half pipe. It's got that shape like a U shape cross section, but then it's got a gradient going down dip. If I have momentum, what'll happen is I'll be sensitive to the global gradient, and I'll have a tendency to kind of go down the half pipe like this. If I don't use momentum, I'm only thinking about instantaneous gradient, I'll have a tendency to kind of go like that, back and forth across the pipe, right? Because I don't have memory, and so I'm not causing the global gradient to have a good influence. In general, what we expect is that momentum is going to smooth out, reduce the noise that we observe within the loss function, its influence on the path. We'll get a nice smooth path. And momentum will help us proceed down dip, down the general slope, and not get too sensitive to local dimples or ravines, kind of like our half pipe right here. We could easily take this methodology and extend it into a stochastic gradient-based method. Now, what's the motivation? What are we doing here? Well, first of all, we may have a lot of training data. And what that'll mean is that the calculation of this loss function may be kind of heavy, computationally heavy. We're going to bring all that data in. We got to do a big calculation. What we could do is we could say, well, let's replace the gradient with the stochastic approximation of the gradient. And I represent it with the L symbol. It's like a realization of the gradient at that location. What we'll do is we'll just retain a random subset of the data. So there's methods to do this. The online method is just one data at a time. Mini batch, you would use greater than one data. And that will give you a realization. Now, I hope you can see that that'll give you reduced accuracy of the gradient. It's going to really reduce the gradient estimation, but it's going to speed up the calculation so you can perform more iterations, more steps, more quickly. And the result is, it turns out we often get a faster convergence with stochastic gradient descent because we can do fast cycles. Now we got to make a choice. If we're going to do mini batch, which we often do, we're going to choose to have so many data within a batch, and we'll balance it. If we put more data in a batch, we get a more accurate estimate of the gradient, but it's slower runtime. For a cycle, if we decrease the batch size, we speed up the steps, we can do more updates more quickly on the location. Now there is a theorem that we would expect to be able to converge to a global minimum for convex loss functions, or either global or local minimum for non-convex loss functions using stochastic gradient descent. In fact, really the accuracy at the end should be very similar to gradient descent. It's just the speed, we'll get greater speed. Now, I could go out on a limb here, and having worked with many iterative type systems, in my experience, I found that including a stochastic component often improves the robustness of the solution. Now, I'm not going to point to any proofs on that, but my feelings are that we may also improve the accuracy of the model using stochastic methods. I've seen so many deterministic methods just get stuck and do crazy things, get caught in feedback cycles and so forth. Okay, so that's it. That is my short discussion on optimization. We've explained fundamental concepts around gradient descent. We motivated it. We explained why we have to do it. We've talked about the step size or learning rate. We've talked about the concepts of momentum. We talked about mitigation of local minimums or getting trapped in local minimums. All of these concepts will be essential as we move into more complicated machine learning methodologies up to artificial neural nets, where these are going to be always used. I hope that was helpful for you. Once again, I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin, where I teach and conduct research in data analytics, geostatistics, and machine learning. And I sincerely hope that this lecture was accessible to you and useful to you. All right, everyone stay safe.